Welcome everybody to another broadcast from Vic South Star Party. My name is Kim Thalasudis. I'm the current president of the Astronomical Society of South Australia. Joining me today is Dr Russell Cockman and Lee from his front yard and Russ from under a sheet or a towel, I believe, outside in his laptop. Welcome. Okay, so before we start, I'd just like to say that in the spirit of reconciliation, our astronomical societies acknowledge the traditional custodians of country throughout Australia and their connections to land, sea and community. We pay our respect to the elders, past and present, and extend that respect to all Aboriginal and Torres Strait Islander peoples today. So, by way of introduction, I know that Lee is on the ASV committee and also supports the website and other IT work. Welcome, Lee. And Russ is the director of the solar section, has been since 2013. And he admits to having learnt an awful lot about the sun during that time, which is a really good thing because he's out there, he's going to be showing it to us today. So I don't think, but you're also the president of the International Dark Sky Association of Victoria. What a contradiction that is.
Well, look, life is full of contradictions, Kim. This is one of them. Anyway.
Well, there you go. That's great to know. And by the way, just out of interest, our society is hosting the director of the Dark Sky Reserve, the International Dark Sky Reserve, the River Murray International Dark Sky Reserve, at our meeting on Wednesday. And that site was, I think it's got 3,200 square kilometres of dark sky.
Right.
It's been preserved in SA, just near Adelaide. So we're looking forward to getting an update on that next Wednesday.
Which is very interesting talk, for sure.
All right. Well, let's get underway then. Let's start with you, Russ. You've got a presentation there.
Yeah.
And people, please ask questions. I mean, this is going to be a pretty fascinating presentation. And we have clear weather, both in Victoria and South, or most of Victoria and South Australia today. So over to you when you're ready, Russ.
Well, thank you very, very much for that, Kim. And well done on your presidency of the of ASA. And so this is so welcome to the solar demonstration from Elwood, which is just 6 kilometres from Melbourne's CBD. Forecast is for clear blue skies today, and no earthquakes are forecast for us. So we should have no interruptions whatsoever. But before we have a look at the sun, it is very, very important to learn a little bit about safe solar viewing. So I have a presentation here that I will start off the demonstration with. A little bit about safe solar viewing. And so here we go. Let's go. So there's our beautiful star, not in the kind of light that we can see. Very, very powerful source of energy. As we well aware, I'm in the sun at the moment. I can feel the heat of the sun on my skin. But there's a serious warning when we consider observing the sun, because unlike the stars we see in the night sky, we must never ever look directly at our sun with a telescope, binoculars, or even our eyes, because permanent injury to our eyes may result from that few seconds of carelessness. Always use proper filtration to reduce the sun's light, and most importantly, the sun's heat, before looking at it. If you've ever held a little magnifying glass in the sunshine and focused it on your skin, you realize how much heat is focused onto that little area of your skin, and that's what happens to your eyes if you're foolish enough to look at the sun without proper filtration. And there are two basic ways of looking at the sun. This is by direct observation, and the first one is called white light observation. And here's an example. So you have a telescope. This happens to have a binocular viewer on it, and this is a refracting telescope. It means it's got lenses up the front, and the safe solar filter goes over the front here, which is a metallized thin sheet of plastic, and basically most of the sun's energy, light, and heat is reflected off that filter back towards where the sun comes from, and perhaps only 0.00001% of the sun's energy passes through that filter, which reduces the amount of solar energy to a safe level. Now, Lee has got a setup at the moment where we can have a look at the sun in white light. So what I'll do is I'll stop sharing, and over to you, Lee.
I've just got a region of interest at the moment on a couple of sunspots, but I'll just take that back out. And oops, nope. Clicking all over the place. So there it is there. So yeah, I've got a Celestron Edge 8, Edge HD 8 telescope with pretty much exactly that same metallized solar film on the front for white light. And I think at the moment it's also, and I've got filters on this as well, so it's also using infrared just to reduce the heat a little bit more as well before hitting the sensor. But yeah, I get a fantastic view of that, and I can take video. That's currently at 3 milliseconds the shot, so it's probably a bit fast for taking video at the moment. But I can take some video of that and do some lucky imaging and stacking and get some what I think are some brilliant solar images.
And Lee, just to cut in, what are you seeing here? Okay, there's the disk of the sun, and what are those little dark things on there?
So there's a couple of no, not in this case. It was last night. I had a dust donut right in the middle of the viewing area. But in this case, it's see if we move the telescope, they move as well. Which typically, if they were dust,
yep,
they would remain in place. So, and they've got another couple up the top.
So we call these sunspots. So they are features on the sun, on this layer of the sun that we're looking at the moment in white light, which is called the photosphere, that dazzlingly bright surface of the sun that lights our world, the photosphere.
So what's the temperature of the sun, the solar surface, and what's the temperature, say, within a sunspot? Do you know that, Russ?
Yeah, about 5,500 degrees Celsius is the average temperature of the photosphere, and those sunspots, although they look dark, they're only a couple of 100 degrees cooler. So it's all a matter of contrast. In fact, it has been said that if you could isolate a sunspot and look at it, it would be as bright as the average photosphere of the sun. So it is all just a matter of contrast, subtle differences in temperature, and which makes things white or dark. That's a nice view.
That is nice, yeah.
Yeah.
Yeah, just stretched. I actually, I'm cutting off some of the light now to give it some contrast. So
excellent. Yep. And is that have you fine focused, Lee?
I did, but really? I do have a bit of trouble focusing sometimes on this, and
okay.
I did focus earlier, but it could well have been out because I've also moved it slightly.
No worries. Could you just go back to that zoomed? Could you just go back to that zoomed view?
Yep. Let me just go back in there. And there.
So, ladies and gentlemen, girls and boys, we're seeing a lovely, very safe view of these sunspots, quite a few of them. And hopefully you can see in the photosphere around those sunspots some subtle light and shade areas. And once again, these are true features on the sun's photosphere, and that's called granulation. Granulation, because this layer of the sun, the energy rises up from the hot central core of the sun, rises up in convection cells. Hot gas rises up. As it rises up, it cools, and then the cooler gas only being a couple of 100 degrees cooler, just is more dense, and it just flows down towards the center of the sun again, and so they are called, that's called granulation. And really, ladies and gentlemen, girls and boys, this is about all you can usefully see with white light filtering. Beautiful views of sunspots, of granulation, and sometimes some slightly whiter areas called faculae on the edge of the sun. And sunspots are given numbers for reference, and this sunspot group we're looking at is called AR2891. So the numbers are given simply for reference for future work on these sunspots, i.e., to refer to this particular group as whatever it did, sort of thing. Okay, okay. Thanks very much for that, Lee. I think I shall go back to my my presentation if it's
Yep,
if you've
not a
shown
problem.
everything you'd like to show. Okay, thanks very much.
You'll have to share that again, Russ.
Yes, okay. I shall do that. Thanks, Kim. Here we go. So that's the white light view. Fantastic for sunspots, some granulation. But if we go on to and so that's similar to what we saw just now. But then we have observing in what is called hydrogen alpha, and so this is the setup that is currently on my balcony at my apartment here. The Astronomical Society's 100mm Lunt solar telescope on a mount that's roughly polar aligned, and at the end here there's my tail. It's over my overhead. My head now is a laptop, and here's a video camera which gives live video that we will see very, very shortly. And if we were doing visual observations of the sun, this is how the sun would appear. A beautiful radiant red disk with sunspots on it, some active regions here around those sunspots, and most importantly, prominences around the edge of the sun. Hopefully you can see those very, very clearly indeed. So in fact, when we use a hydrogen alpha filter to look at the sun, we're actually looking at a slightly different layer of the sun. This layer is slightly above the photosphere, slightly cooler, and it's a region which is called the chromosphere. Now, for those of you who are listening to Rod earlier, he mentioned the chromosphere, which becomes visible just a few seconds before a total eclipse of the sun, when the moon has covered up the brilliant photosphere, but this little layer of chromosphere being above the photosphere gets covered by the moon just a second or two after the photosphere gets covered up, and it is the source of these beautiful red prominences that we see around the sun's disk. Now we talk about solar activity, and it is now well known that sometimes when we look at the sun over here on the left, there are lots of sunspots. Other times when we look at the sun, there are no spots at all. And this was sort of discovered in the early 1800s, and with more observations, more data, it was discovered that the sun has an 11-year cycle. So on the vertical axis here is a number called the sunspot number. Basically count the number of sunspots visible on the sun and do a little bit of mathematics to it, and do it day by day. And you can see that over the years, 1760, 1880, the number of sunspots visible rises to a maximum, then goes down to effectively zero, rises up to a maximum, goes down to a zero, roughly every 11 years. On average, 11 years, but it could be 13, it could be 9, but on average, 11 years. And here it is, continuing from the 1880s up to the present era, the solar cycle. And you'll notice that solar activity is measured by the number of sunspots. It's not constant either. It varies from one cycle to the next. And this was, and in fact, these solar cycles are given numbers. This was cycle 24, this one here that I've indicated, and continuing right up to now. You can see that from 2010 to now, the sun has gone through another solar cycle up to a maximum, actually 2 maxima, one here and one there, before steadily declining in sunspot numbers down to a time for the latter half of 2019, when there was barely a sunspot visible on the sun for months on end, barely a sunspot visible. But the sun has woken up, and from 2020 onwards, you can see the sunspot number is rising up, and we're expecting another solar maximum somewhere around late 2024 into 2025. Now, what does all this mean? It doesn't mean that the sun's heat and light varies, but it means that the sun's magnetic characteristics are varying over this 11-year cycle, because it's the sun's magnetics which changes the number of sunspots, changes the number of flares that the sun gives out, changes the visibility of the southern lights or the northern lights. So it's all down to the magnetic variability of the sun, which really was only discovered through launch of solar probes like SOHO, which is the Solar Heliospheric Observatory, or the Solar Dynamics Observatory, where these observatories in space could actually measure the magnetic characteristics of the sun and tie it up with the changes in sunspot number, amongst other things. Okay, so that, and what really is a lead-in to what we're going to see today. So the sun's activity is on a rise. It's nowhere near solar maximum, and so let's see what the sun has got to offer today. In short, so I shall share again, and please keep those questions coming. I love questions.
So when is the next solar maximum forecast for?
It's not predictable as such. We can just give a, when I say we, solar scientists, a window of 2024 to 2025 sort of thing. Okay, so it all depends on what kind of model is used for it, but we are a few years off yet.
Okay.
So here we go. Hopefully you can see that. This is the view of the sun through the Hydrogen Alpha telescope. Now, one thing I didn't mention is this video camera is a monochrome camera. It only shows levels of grayscale. In fact, it shows better images of the sun than if it was a color camera, because bearing in mind the eye is very sensitive to changes in the shades of gray, but not so sensitive to changes in levels of red. So looking at the sun in shades of grey does highlight features far more effectively. So here's the view through the video camera. Here's the sun up here. So now I'm going to get my mount control and move the sun towards the center of the field of view. There we go. I'm moving the mount now, which is moving the telescope, bringing the sun into the field of view. So this is an absolute setup, ladies and gentlemen. You notice the sun is fuzzy. That's because I haven't focused the telescope. Very, very important to focus. So I'll focus it now. Just adjusting the focuser. You can see the sun is starting to get a little bit sharper, a little bit sharper. There we are. We can see some sunspots now.
Wow, look at that.
Also, ladies and gentlemen, as I said, this is how we would set it up. Now you notice that the sun up here is really burnt out. We would say it's overexposed, but down here it's nicely exposed, and this is because the hydrogen alpha bandwidth, the amount of light that the solar telescope lets through, is very, very narrow, and the sun is rotating. So it means that some parts of the sun can appear darker than other parts. So the wonderful feature of the solar telescopes is that they have a tuning facility. So I'm just going to be cranking in the tuning now, and you'll see that the bit that's overexposed is now becoming better exposed. It's losing its brightness, and I'm looking for a setting which is completely a manual, just screwing into a knob to get the sun pretty well evenly exposed. And I reckon that's about it, actually. I will give the camera a little bit more exposure. There we are, perhaps a little bit more.
So this is a special solar telescope, Russell.
A hydrogen alpha solar telescope,
Right.
yes.
So it's not, is this something you can add to a regular telescope, or do you have to buy the telescope
you,
as is?
Well, a very good question, Kim. And modern systems, yes, you can take a standard refractor that you'd use for observing the night sky, and you can put a hydrogen alpha filter on the front of it to convert it into a solar telescope like this. And there are some companies out there that do exactly that. They provide a dual purpose telescope that is suitable for night viewing and also suitable for solar viewing. So please bear in mind, this telescope, as set up, it's only good for solar viewing. It's a single purpose telescope. I reckon it's a brilliant idea to provide or offer a telescope that can do both things. Can be used for nighttime viewing and for solar viewing as well. Not only in
It's
hydrogen
also,
alpha, but in other colors as well.
in addition to the hazards of looking at the sun, or pointing your telescope at the sun with a regular telescope, and the personal hazards, you'll also destroy it almost certainly,
Correct.
I imagine, as well. So don't ever point at the
Absolutely.
sun unless you absolutely know what you're doing. But it's interesting to know that you can actually convert or
Yes.
adapt a regular telescope to a solar
Yes.
telescope with the right gear.
Yes. The thing that does the filtering is called an etalon, and these can be designed for filtering particular bands of light. So you can get a hydrogen alpha etalon, or you can get a calcium etalon, showing the sun in a different color and observing a different layer of the sun as well. So it's a bit like an onion, actually. You look at a different color and you're seeing slightly different characteristics of the sun. So here's the full view of the sun, and ladies and gentlemen, girls and boys, this is probably has to be the safest way to observe the sun, because you're not actually looking at it. It's a video view of the sun in effectively real time, although it takes 8 minutes and 20 seconds for light to reach the Earth from the sun, but it's as close to real time as we can possibly see. So there's the disk of the sun, and you can see, and I'll show you some close-ups as we go along, but here's a sunspot group here, and here's a most likely is a flare taking place. This bright white area, which is an indication that area is a few hundred degrees hotter than the average chromosphere temperature, and that appears white to us. So this is we call this an active region because magnetic lines of force are coming through the chromosphere and creating sunspots, and those magnetic lines of force are joining together, liberating huge amounts of magnetic energy, stored energy, which creates flares, explosions, and in fact, this sunspot group over here, which has got a number of 2887, I think it is. I'll just check my my crib sheet. Yep, 2887. A couple of days ago, when it was in this position, because the sun does rotate from here or in that direction, but that sunspot group was about here, and it erupted in what is known as an X-class flare, which is a very powerful flare, which sent a huge cloud of plasma, solar stuff, racing in the direction of Earth, and it was expected to arrive by now, but it might arrive tonight. And if it does, southern Australia and New Zealand will be perfect, and Tasmania. I'm not going to forget about the Tasmanians, but and the South Australians. It will be perfectly placed to hopefully observe the display of the aurora australis. So this is stuff that left the sun 2, maybe 3 days ago. Takes its time to get to Earth, but when it interacts with the Earth's magnetic field, it can create displays of the aurora australis for us in the southern hemisphere, and the aurora borealis for residents of the northern hemisphere of the Earth.
Oh, that's fascinating. The that sunspot group on the right, is that the one that we were looking at initially with the
Correct.
Lee's
Yes.
telescope?
Through Lee's. I've got a slightly different orientation to what Lee has got. But ladies and gentlemen, here's our full sun. Subtends about 1/2 of 1 degree angle in the sky. And let's see what prominences might be visible around the edge of the sun. So I'll just change the exposure on the camera, crank it up fully, so I'm overexposing the chromosphere in the hope of bringing out prominences around the edge. And as you can see, it doesn't look like there are many prominences visible today, but I have a little bit of more oomph that I can provide. And you can see that, yes, there we are. There's a few prominences, fairly small ones, becoming visible around the edge of the sun here. One over here and one here. Now, which is a little bit disappointing because a few days ago, there were lots and lots and lots of prominences around the sun, but I do have a video that I took then that I can show at the end of this
Now,
demonstration.
to see
So
the
that you
prominences,
can-
all you did there was effectively change exposure or gain. Is that right?
The
Russell?
gain, correct. Yes.
Okay.
There's something
make it-
something significant there
To make
on the right-hand
fainter
side.
features.
Oh, yeah,
And
on the
over
right-hand
here,
side.
look at this. Yes.
Oh, yeah.
No worries, ladies and gentlemen. We can zoom in though on those. No worries at all. This is just a teaser.
Well spotted, Lee.
This is just a teaser or a tempter. So I'm just reducing the exposure now. So we've got our chromosphere well exposed. And here's a point of information for you, ladies and gentlemen, and girls and boys. So here's the diameter of the sun across here. The sun is effectively a sphere. And imagine you can fit 109 Earths across that diameter. 109 Earths will fit across the diameter of the sun. And that means over 1 million Earths will fit or could fit inside the sun. Just to give you an idea of how big our sun is compared with the Earth. So when we have a look at one of these sunspots, we think, oh, that's not very big, is it? You know, curling up the corner of your mouth, that's a pretty small spot. But when you think of it, 1 or 2 Earths could probably fit inside that, with some room to spare. Okay, so it's always important to put things into perspective. Our sun is a beautiful star and slightly larger than average star, and how beautiful it is to be able to study a star up so close. Okay, so there's our sun. We've seen the full disk. Okay, perhaps I should point out some largish overall features here. So here's an active region. That's 2889, I think it is. 2887 here. Anyway, like I forgot that number, but never mind. But if you look very, very carefully, you can see that the entire chromosphere is mottled. Some lighter areas and some darker areas. So that's exactly the same granulation that we saw in the white light image. Only this is slightly more contrast to make these features a little bit easier to see. And you can see a feature here, this dark feature here, and features over here. These are called filaments. So these are actually prominences seen silhouetted against the chromosphere. And because prominences are a little bit cooler, they're a little bit further from the source of energy. They're a little bit cooler than the average temperature of the chromosphere, and because temperature makes things light or dark, that difference in temperature is enough to make these filaments stand out as slightly darker patches against the brighter chromosphere. Okay, let's home in on this active region here. So I can simply do that by drawing a field of view around it, doing that. Well, that looks quite small, but I can magnify it. Bang, there we go.
Ooh,
How good is that, eh? Now
excellent.
I'm going to do a little bit of fine focus on this because I want you to see, and I'm just touching the focusing tube right now, just finding the sharpest focus I can. Now, isn't that gorgeous? Don't all shout at once, but certainly it is. How gorgeous is that? So a couple of sunspots here. Magnetic lines of force are breaking through the chromosphere, and when they break through, they create slightly cooler areas around it, and we see those as darkness. And here we have a couple of explosions taking place on the sun, which we call flares. These are probably fairly low energy flares, ranked probably a high B class or a low C class, fairly low energy. that X-class flare I mentioned earlier on would be about 1,000 times more energetic than a C-class flare or a B-class flare in comparison. But nevertheless, these flares are, what can we say, are producing prodigious amounts of energy, which can create prominences, these so-called flames or apparent flames that jut into space, and filaments as well. But have a look. So here's the general chromosphere around here, just general little mottling light and gray areas. But in the region of a sunspot, the chromosphere starts to get structures. You know, it starts to show curved-like structures and structures going out. That's because the magnetic lines of force are very, very complicated around active regions, and plasma, being charged particles, has to follow those lines of force if it's going to move at all. And so these structures here are actually indicating the magnetic lines of force coming through the chromosphere. And I guess, look, a lot of us have, when we were young, got a bar magnet and put some paper on it and sprinkled some iron filings on the bar magnet, and you can see the magnetic lines of force coming out of the North Pole and the South Pole of that bar magnet. And that's exactly what we are, in like sort of terms here, are seeing the magnetic lines of force coming from deep inside the sun and breaking through the sun's chromosphere.
So, Russell, is it common for sunspots to appear in pairs like that?
Absolutely. Very good question, Kim. That's right, because magnetics must always have a North Pole and a South Pole. All right, so one of these sunspots will be the magnetic north, and the other will be the magnetic south of that magnetic line of force that is coming out. Yep. So, and that's a fairly simple looking sunspot pair, but when you realize that the more complex sunspots get, the more complex the magnetic fields are that are creating those sunspots. And the more complex a sunspot is, the more magnetic lines of force there is available, and the more stored magnetic energy there is. So big sunspots, complex ones, are generally the source of these large and energetic flares that we are looking forward to as the sun rises to solar max in 2 to 3 years' time. Fantastic, eh? As I said before, that looks like a small spot, but probably 1 or 2 Earths could fit inside that with no problem at all. And the temperature of this flare might be well over 6,000 degrees Celsius, and inevitably blasting a little bit of solar stuff into space. Not enough to reach Earth, but certainly enough to reveal a prominence in due course. Okay, so let's have a look at another sunspot group. So here's our sun again. Here's a beautiful region over here. So I'll just draw, I think I'll draw a region there. We'll do the same thing and zoom in. Bing. One thing I haven't mentioned is that the sun is jittering around. And it looks like it's sort of sharpening and getting fuzzy. That's actually an effect of the Earth's atmosphere. It's not directly due to the sun itself, but it's simply because we're looking through the Earth's atmosphere and observing in daytime where the sun's energy is being absorbed by buildings and roadways, etc. Those things are getting hot, causing air to heat up and rise up, and it causes these what we call seeing. It causes changes in the light path that gets to the telescope, and we see that as a little bit of blurring, fuzzing, and boiling. So this sunspot here, which is 2887, it was the sunspot that was responsible for the X1 flare that erupted 3 days ago, which sent a huge cloud of charged gas earthwards, and we're still expecting it to arrive. and hopefully it will arrive tonight. So if the skies are clear, ladies and gentlemen, girls and boys, get away from light polluted city streets and what have you, and try and find a nice place with a nice dark view to the south. You might see some colours in the sky, the aurora australis, and lots more to look forward to. How good is that? Now, I should also point out that the sun, like most things in the universe, is rotating. It takes about 27 days for the equator of the sun to do one rotation, but that period of time increases as we go from the sun's equator towards the poles, and so a sunspot, if there was one near the pole, would take about 35 days to complete the rotation. Unlike us standing on the planet Earth, whether we're at the equator or at the pole, it still takes 1 day for us to do one rotation. That's because the Earth is a solid body. Now, solar scientists back in the early 1800s, through careful observations of sunspots and how they appear to change position over days, realized that, crikey, the rotation period of a sunspot depends on how close to the sun's equator it is. So therefore, simply based on these observations, people concluded, quite rightly, that the sun is not solid, but a huge ball of gas. And how incredible is that? Simply through observing how long it takes sunspots to rotate, they were able to confirm, which was a massive observation or conclusion, that the sun is not a solid body, but a huge ball of gas. And of course, then that raised the question, well, gee, if it's a huge ball of gas, how can it have supplied energy for so many millions or even billions of years?
So we have a question there. I have a question there from Peter. Russ.
Peter?
Yeah, he just wants to clarify that black spot to the left is what we're referring to as a sunspot, right?
This is a sunspot. Yeah.
Yeah.
Yep.
So
that's a sunspot. That's a flare here.
Yep. So the bright ones are flares, and the black ones are the sunspots.
Yep.
Okay.
So the flares are magnetic energy just being liberated and heating up the surrounding area a little bit, and there we have it. Yep. So lots and lots of granulation here, lots of whitish areas which are active regions. Active, we call them, because they are liberating energy, a little bit more energy than the average region is doing. And as I say, these active regions are the regions that we define as solar activity.
So those regions are actually changing with time over the course of what, minutes or hours? If we came back and had a look.
Well, over 15 minutes, half an hour. Yes. Okay. So if we could have a look at this region in an hour's time, we would probably find that this region would not be as bright then as it is now, because flares only last for 20 minutes, half an hour, all depends on how powerful they are. And over a period of days, sunspots will change their appearance, because the sun is just an incredibly dynamic object. It's just a huge source of power, and that power changes in a period of hours to days. How fabulous. A filament here. So let's go back and see what else we can see. Keep those questions coming. There's our sun. Filaments here, granulation, lots of active regions here. Another filament there. Let's just zoom in on this filament and see what we can see. Here we are. Filament here, filament there. Now, it will be amazing to learn that these filaments aren't there for no reason at all. These filaments are there because there's a magnetic line of force which is holding up the gas that is that filament. And sometimes you may get that those magnetic lines of force will reconnect, is the scientific term. And as they reconnect, all that stored magnetic energy is liberated. I don't recommend you do this, but if you just take one of your little, say, AA batteries and just short out the two terminals, that wire, the conducting wire, will get very, very hot indeed. So in other words, you've got stored energy in the battery, but if you short it out, all that energy is then liberated as heat in the conducting wire, and that's effectively what we're seeing here. We have magnetic lines of force which are separated, and that all that stored energy is stored. But when those two lines of force come together, reconnect, all that energy has to go somewhere, and it ends up as heat, and that filament can be blasted into space as what we call a coronal mass ejection, and hence could lead to some minor auroral activity visible on the Earth, as long as conditions are correctly set up for doing that. Yep, some filaments. Now we think, oh gee, they're pretty small, aren't they? But I reckon we could probably fit 10 Earths along this filament here, just to give you an idea of the size of it. Remember the diameter of the Earth is about 14,000 kilometers. So 5 Earths, we're looking at about 70,000 kilometers.
So I think you've answered this question already, Russ, and the temperature variation.
Yeah, just a few hundred degrees. A few hundred degrees. So a slightly darker region like this is a few hundred degrees cooler than average temperature, and an active region will be a few hundred degrees hotter. And as I said, that's just enough to make things look white or dark in this particular band of color that we're looking at.
But the absolute temperature is around 6,000 degrees C.
Close, yeah, 5.5, 6,000. Yeah, that's sort of ballpark. Yep.
Okay.
Hopefully you're enjoying these views, ladies and gentlemen, because look at those really delicate structures that appear when there's a moment of quite still air visible. And the wonderful thing about taking a video is that because at the moment my frame rate, which is this number over here, I've set a maximum of 100 frames per second. So in other words, that's 100 still frames every second, which are combined together to make this video. So if I recorded this video for 30 seconds, that means I've got 30 times 100 still frames that I can work with. And it's inevitable that quite a few of those still frames will be taken when the Earth's atmosphere is still and sharp, getting sharp images. So this is the beauty of taking videos in order to put that video into a program which selects the sharpest of those frames, puts them together, stacks them up, and from that, absolutely awesome still images of whatever, the sun, the planets, can be achieved. And it's just a fabulous technique for astrophotography of bright objects. Keep those questions coming. So there we have it. So I think I will expand the exposure, crank it up, and we'll just home in on one of the prominences. As I said, oh yes, there's a nice prominence over here.
Oh, this is the one you were teasing us with earlier.
Oh, look, I'm a teaser. There we are. Look at that. I'll just back off on that again a little bit. Look at that. Yep. Yep. I feel like I can almost reach out and touch it, but I shouldn't do that because it's still very hot. Okay, but there you go. What beautiful structures are present in that. So this is clearly has been an explosion on the sun, and put into context to some extent, hundreds of thousands or millions of atom bomb blasts all combined together to produce the energy to create one of these things. It is just Prodigious. Awesome. And I know that word awesome is bandied around, but this is truly awesome. There's several bright knots in it, here and there, and all this structure. All that shaking around is perhaps me just banging the my patio floor, or minor earth tremors going through, ha ha ha, or most likely just the Earth's atmosphere. How awesome is that?
So is the
Now, ladies and gentlemen,
prominences following the magnetic field lines as well?
in general, yes.
Okay.
Very, very complex. Yep.
That one's sort of it's got a bit of an odd shape compared to some I know we've seen before. Would it be possible that that's actually two prominences?
Very likely, Lee. Yeah, very, very good that we're effectively seeing the sun in two dimensions, a two-dimensional view. We should remember it is a three-dimensional object. So there is a front and back kind of perspective that we're not picking up here, but that could well be two prominences overlapping. Yeah, two arcs, in other words.
Yeah, because you can see just below and to the right, there's just a tiny little speck that no, down and to the right. So to the right now, a bit further across. Out in yeah, just there, right where the mouse is.
Right.
You can sort of see a little bit just under where the mouse is.
Okay, well, I'll crank up the gain a little bit more.
Yeah, as though one of those sort of parts is following that line out and going back around the back.
So these prominences are clearly separated from the sun. You know, there's the actual edge of the sun just there. One and a prominence down here. But if I increase the gain, that tends to sort of scatter light within the chip that I'm using and makes the edge of the sun expand a little bit. But there we have it. I'm going to see what else is present on the sun using this. It's probably the most interesting feature. There we have it. So I'll just return the exposure to normal for the chromosphere. Oops. And reduce the gain up here. Lots of things to play around with. Oop, too much.
So we have another question here, Russ,
Certainly.
just quickly. And I think if I read this correctly, can what we're seeing here affect our temperature on Earth and in particular impact climate change?
Well, that's a can of worms. Well, look, climate scientists are aware that, okay, the sun has an 11-year cycle. However, the sun's heat and light does not change very, very much at all during that 11-year cycle, perhaps 0.1%. Now, that is not going to have a substantial sort of cyclic effect on our climate. That very slight change in energy output, and by energy I mean heat and light. But bearing in mind the sun's magnetic strength varies from very, very low to relatively high over 11 years. And that can affect the Earth in other ways. So I do not want to go into much detail about it, but I reckon there is a need for more research into the changes in the sun's magnetic properties and how that might affect the Earth. And the reason being that there was a time from about 1650 to about 1720 when there were effectively no sunspots visible at all. But when I say when a sunspot appeared, that was big news. You know, it was on front page on newspapers, etc., etc. There's a sunspot on the sun today, and that's not a police lyric, but and it just so happened that during this period, which is called the Maunder minimum of very low solar activity, this led to very, very cold winters in the northern hemisphere. Winters so cold, and this is not every winter during this period of time, but there were cold winters when the Thames froze over, and they were able to hold ice fairs on the frozen solid, at least on the top of the Thames. And so that in many ways is a little bit too coincidental that during a time of extended low solar activity, there were unusually cold winters in the northern hemisphere. And as it is erroneously termed a mini ice age, but the average temperature only was probably half a degree cooler than average. But that was nevertheless enough to cause these unusually cold winters from time to time. And I have to stress, not every winter was cold enough for the Thames to freeze over and other rivers, but there were more times than not when this did happen. So to me, that is a bit too coincidental. So it tends to suggest that perhaps the sun's magnetic cycle can have, if it is a prolonged lull in solar activity, can affect our climate. So that's probably all I'll want to say on that, but it is a very controversial situation.
Oh, understood. Thank you, Russ.
Great. Okay. Well, I think that's about all we can see on the sun today. But if you wouldn't mind, I'll show you a video of just a few days ago of the sun, and we'll finish off there. So I'll stop sharing this.
Thank you.
In the meantime, Russell, we've got a one of our regular members. Actually, I'm not too sure of their name, but Make More Memories wants to know if our next raffle is going to be a lunt.
Well,
what do you reckon?
That sounds like a pretty good idea. Really, absolutely. Get more people involved in solar observation. Yes, that's something to put to our committee. The 26th of the 10th. So I'll play this video and then I'll share it. Just make sure it's the right one. And then we will finish off. Just play some music.
I don't think I've got any that is royalty free at the moment.
Oh, that's a shame. Gee, my video program doesn't seem to want to load up at the moment. How nuisance is that? Anyway, I'm asking it to play. Here we go. Finally.
Maybe is it playing or?
It's trying to play. Isn't it funny? It worked yesterday in as a practice.
Yeah.
It's just not coming up with anything. What a nuisance.
Can you see it on your computer, Russ?
This one is.
If you can see it, we can share what you're seeing.
Yes, I will indeed. I'll share that now. There we go.
Okay, I'll add it to the stream now.
Thanks a lot. I'll just let that cycle through. Once again, just playing around with the gain and the exposure to bring those prominences out. Hopefully you're able to see that now. Oodles of prominences around the
edge look at them.
Sun. Just 3 days ago, the 26th. Well, that's 5 days ago, but oodles of sunspots.
So what was the time frame of this video?
30 seconds.
Like how long was the overall time of that that it took to take that?
30 seconds.
It
Just
actually
30
was only 30 seconds. Oh,
Only
okay.
30 seconds, yes. But I played around with the gain. So I
Right.
started off with the settings just right for the chromosphere, and then I cranked up the exposure and the gain to bring the prominences out to be burnt out effectively, just to highlight. Well, and this one here was very impressive because it was as bright as the chromosphere, and that's a very good indication that solar activity is rising quite steadily. Because normally during low solar activity, the prominences are quite a deal fainter than the chromosphere, and they only show up a little bit like today when the gain is cranked right up. But when we go back to the start, there we go. You can just see it, the normal exposure. So that is a wonderful thing as the solar activity rises, that the prominences will be seen with the normally exposed chromosphere. So that is the beauty of solar observation, ladies and gentlemen, boys and girls. The sun, our star, it changes by the hour, changes by the day, and changes by the year. So it's always giving us something different to enjoy.
Well, that was excellent, Russell. And Lee, thank you very much. Well. That was...
okay, I'll stop sharing that, Kim.
I'm sure that's got a lot of people interested, actually. I mean, it's quite a dynamic thing. You can do it during the daytime and still get your sleep, right?
Absolutely, that's exactly it. Well, I am an astrophotographer as well, Kim, so I do know what late nights can do.
Yeah, I didn't get home till 2 a.m. last night after that live stream event, and I'm feeling it today, I'll tell you. That was fantastic. I've not looked through
very, very welcome.
the sun for a long, long time. And back then it was the wrong way to do it. And you don't even want to go there. It's just way, way too risky. So there are proper telescopes, dedicated telescopes, and again, I imagine there's live streams on the internet as well, apart from this one, where you perhaps do get almost 24/7 coverage, if that's possible.
There are, yes, and if anyone is interested in that, please, I don't know, contact the ASV or ASA, and we'll be happy to provide some links to what is available out there for almost real-time solar observing. There's so much available, it's terrific. And it is a wonderful time to be alive just to be alive with all the information that is available to us, just at the touch of a button through the internet.
It's a combination of the technology and the availability, I guess, that makes a huge difference.
Yeah. Something you actually touched on, just going back a fair bit, Kim. You sort of said, you mentioned you imagined how dangerous it would be for the telescope itself, like normal telescopes as it was. Mine's, as opposed to the Lunt, mine's a good example of that. Where it was a few weeks ago, I was getting set up for some morning viewing. And I didn't have the solar filter on the front, but I had already slewed around thinking that I knew I would have to adjust before I got, on the sun. But I just happened to, because I move the scope around quite regularly, somehow I must have, even in this different position, had perfect polar alignment, and it had gone straight to the sun without having my solar filter on. And I've gone and put it on. And later on, I'm looking at this, at the view, and I'm thinking, I don't know what these lines are on the thing. And I thought, we've got these little icicle lights hanging down from the garage. I thought maybe it's those. That's probably what it is. But as the scope moved around further, still there, and I thought that can't be right. And anyway, I had a look a little bit later on, and I pulled my filter wheel apart to clean it, and realised my red filter had cracked. So just that few seconds of having the light from, obviously magnified through the scope and hitting the red filter was enough to raise the temperature probably a few hundred degrees, and it's just gone
Yes.
crack. And I'm extremely lucky that it didn't damage the camera at the at the other end of it. So
Yes.
yeah.
Well, I lost a T-shirt when I was a teenager doing something similar. remember the old? You used to get these refractors in department stores, and they had like a solar projection system in them where you project onto it, and it was at right angles, right? And I think I'd taken off the right angle prism, and whatever I was doing, and then I just noticed all this smoke coming from my T-shirt. So I'd copped it, and it's instant. It's extremely hazardous.
Yes.
Right.
Yeah.
So,
and I'm always mindful now, like putting the solar filter on straight away, but also because I've still got a finder scope on and my guide camera, I cover the guide camera so I don't damage the camera there.
Yeah.
But with the finder scope, I also, as soon as I've slewed around, I actually use my hand behind that to see if I'm in roughly the right spot. But I also then take my hand back and forth just to make sure I'm not seeing it go to a point somewhere that's going to start a fire in the garage. So, you just got to take those measures.
No, extra.
But I think the summary is that it is very dangerous to observe.
Absolutely,
if there are any doubts about whether the equipment is capable of doing it, the answer is don't do it. Until you're absolutely sure that you understand the dangers and that the dangers are mitigated. Absolutely.
All right. So Kevin has put up a link, and that's to the Solar Dynamics Observatory website, and I think that's a good place to go as well.
That is a terrific place to go to. Thanks, Kevin.
Resource.
Terrific place. Yeah.
Okay. Well, that's just over an hour, so I think we are done for the day. And in fact, for Vic South for 2021.
Yes.
Our online version. So this is the last presentation. So thank you, Russ, and thanks, Lee.
Very
wonderful presentation. Fascinating. I'm sure it's going to stimulate a few people to get out there and do some solar astronomy. That was great.
Fantastic.
Have a great day and enjoy the sunshine, especially you folk over in Victoria. We get a little bit more, but not much. But make the most of it. And till next time, I guess, till next Vic South, wherever that may be, and hopefully it's in person.
In person.
That'll be something unique.
Yeah.
All right. And until then, I'll just sign off. And until then, cheers.
Bye, everyone.
Bye.
Take care.
Cheers.
Stay safe. Bye.
Bye.